A company owns and operates an old inefficient power station. A major problem has just occurred at the power station which needs to be repaired for the power station to continue operating. The cost of repairs is $600,000, which would keep the plant running for another year, at which time even more expensive repairs would be required. However, the operating profit, not including the cost of the repairs from keeping the plant in operation, has a net present value of only $500,000. If these were the only considerations, then the company would shut down the power plant, as a major overhaul is required in 1 year's time, and the cost of this overhaul would be larger than the NPV of the future income of the plant. The government where the power plant is located is planning to join a multinational carbon trading scheme in 1 year's time. The power plant will need carbon credits to continue running after that time. The amount of carbon credits it requires has a current market value of $1 million. The government has promised the company that when the carbon trading scheme starts in 1 year's time, that it will give the company the right to buy those carbon credits at $1 million, no matter what the market price will be, as long as the power plant is still operating at that time. There is nothing to stop the plant from shutting down and selling its carbon credits as soon as it buys them, or not buying them from the government if they're not worth that much. The price of the carbon credits has been quite volatile. The prices at the end of each quarter that the market has been operating are given in the table below. The risk-free rate is 3%, and the values of the carbon credits for the last 10 months are shown in this table. Should the company continue operating the power plant so that it retains the rights to buy the carbon credits? Solve the problem using a binomial lattice with 4 time steps. First, we need to determine the volatility. Step 1 is to take the ratio between successive prices and take their logarithms. So we've got the prices here, and the formula we need to do is yi is equal to the logarithm, as in natural logarithm, of each p-value divided by the p-value before it. So, if we take 35 and 30, so that's going to be equal to the logarithm of 35 divided by 30, which is equal to 0.1542. So we put that up here. Y1 is equal to 0.1542. So Y2 will have Pi divided by Pi minus 1 is 32 divided by 35, and take the natural logarithm of that. So we'll get Y2 is equal to minus 0.09. Now what's happened is because the 32 is smaller than the 35, when we've calculated this out, we've got a number in here which is less than 1. So therefore, when we take the logarithm of it, we get a number which is negative. So on average, if this is not increasing or decreasing over the long term, we'll find that we'll get an average of 0 here. Okay, so now we'll work out the rest of them. So we've got Y3 is equal to minus 0.247, which is even more negative than this because this one is much less than this one compared to this one and this one. Okay, now from these numbers, we can calculate the volatility. The volatility is actually the standard deviation of these numbers. So sigma is equal to square root of 1 on n minus 1, the sum of yi minus y bar all squared. So this y bar, of course, is the mean. So the first thing we need to do is to work out the mean, which is pretty straightforward. We add these numbers up, and there's 9 of them, and so then we divide by 9. So we've got y bar is equal to 0.023. So now we can substitute that in there. We can put all these numbers into here. Obviously this is best done by a spreadsheet, and our answer will be 0.162. Now this is the quarterly volatility because these are quarterly prices. If we had annual prices, then this would be the annual volatility, but we don't. So we need to change the quarterly volatility into the annual volatility. The way we do that is, let's put a little Q down here so we know that's the quarterly volatility. So we're going to say that the annual volatility is equal to the quarterly volatility. Now, there are 4 quarters in a year, so we're going to multiply that by the square root of 4, which gives us an answer of 0.323. Okay, you can see I've had a bit of rounding up here. Now, the next thing we need to do is we need to work out the time step. So we're going to use 4 different time steps. So the size of the time step is equal to the total time that we're going to analyse divided by the number of time steps that we're going to use to do that. So the total time is going to be equal to 1 year. The number of time steps is equal to 4. So we have our delta t is equal to 1 quarter. Okay, so now we've worked out our sigma and our delta t. We now need to work out what are the amounts that it will go up and down in our binomial lattice. So we calculate u. U is equal to e to the minus sigma delta t, which is equal to e to the minus 0.323 times 0.25, which gives us 1.175. The easy way to calculate d is it's the reciprocal of u. So therefore d is equal to 1 divided by 1.175, which is equal to 0.851. So now we know how much our tree goes up by and how much our tree goes down by. Next, we need to work out what is the probability that it will go up and what is the probability that it will go down. So P of U is equal to E to the R delta T minus D divided by U minus D. So what you'll notice is this looks a lot like a linear interpolation formula. So now we can substitute our numbers in. So this is equal to E to the R is the risk-free rate. And we said earlier that that's equal to 0.03. Delta T is equal to 0.25. D equals 0.851. and we said U equals 1.175. So we subtract 0.851 again because we've got to subtract U. So this gives us 0.483. Now, to calculate PD, the easiest way to do that is simply, since PU plus PD has to equal 1 because there's only two options, we can say this equals 1 minus PU, which equals 1 minus 0.483, which is equal to 0.517. Okay, you might be looking at this and saying, hey, wait a sec, it's more likely the prices are going to go down than they go up. But do remember, this number is bigger than 1 more than this number is smaller than 1. So these two things might cancel out a bit. Now that we've got these values, we can start drawing our binomial tree. To start off with, we're talking about getting $1 million worth of carbon credits in 1 year's time. So we start with the $1 million. Now this could go up or it could go down. If it goes up, we're going to multiply it by 1.175. So that gives us $1,175,000. On the other hand, if it goes down, we're going to multiply it by 0.851. So that gives us $851,000. Then, after 3 months, it could either go up or it could have gone down. If it goes up, we'll multiply this number by this number again, and this time we're up to $1,381,668. If it comes down, we're going to multiply it by this number. But remember, we said this times this gives 1 because they're reciprocals. So if we multiply it by up and then we multiply it by down, we go back to $1 million. We could have done the same calculation by multiplying it by down first and then multiplying by up, and we'll still get $1 million. Now we multiply this number by the D value, which is 0.851, and this will give us $723,763. Once again, we could go up or down. So we've got 1, 6, 2, 4, and $72, or we've got $1,175,000, 444, and we've got $850,000, 743. Okay, now we don't need those numbers anymore, we just need these numbers. Right, now we know how much the carbon credits are worth in 1 year's time. They could be anything from $1.9 million down to a little bit more than $500,000. The question is, how much are they worth to us? Now, in order to get these values, we have to pay $1 million. So, if we can buy $1.9 million carbon credits for only $1 million, we make a profit of $909,000 Similarly, if we could buy $1.3 million worth of carbon credits for only $1 million, we'll make a profit of $381,668. If we could buy $1 million worth of carbon credits for $1 million and then sell them for $1 million, we don't actually make a profit. However, if we were to buy $723,000 worth of carbon credits for $1 million, we're losing money. We're not going to do that. That would be silly. So this is actually worth zero to us as well. Similarly, this is an even worse deal. So once again, we won't take the deal, and so it's worth $0. Now we can work backwards and calculate the rest of our tree. So now we know what's going to happen in 1 year's time. We need to work back through our binomial tree to work out what's happening in the present. So for each step, we take this value and this value to calculate a value here. So what we've got is our new option value is equal to, well, it's a decision tree. So it's option value from up times the probability that it actually went up plus the option value for going down times the probability that it went down. But that's not enough. This is future values. And as we know, to convert future values into present values, we need to use discounting. Now in this case, the formula is we times that by e to the minus rt. Now, e to the minus rt, where does this come from? The basic idea is e to the minus rt is equal to, remember we've been using 1 on 1 plus I to the n? Well, it's like that. This is what you get if you make I really small and correspondingly make n big. So instead of putting the interest rate for the year, we'll put the interest rate for the day, and then we'll put n as the number of days. We'll get closer and closer to this. Of course, you can get closer to this by going by seconds instead of days. So that's where this formula came from. It's just the normal discount formula that we've been using so far. So now, let's substitute our numbers in. So this gives us 909,006 times 1.175 plus, and we're in square brackets here, 381,668 times 0.517 times e to the minus, r was 0.03, okay, times 0.25. So this gives us $631,545. So we copy this value into this slot down here, $631,545. Now we will continue using the same formula for the rest of these values. So this one is 182,916. Now naturally, that will be 0, because 0 times something plus 0 times something gives 0. Similarly, we'll get another big 0 down here. And we keep working our way back through the tree. And then for the last step, we multiply this by this plus this times all of this, and we end up with $134,210. Now, the question is this option value make it worth running the power station? So we need to think about that.